so for inert electrodes, oh, I'm missing a page. No, I'm not. I grabbed them out of order. Okay, so here's an example. Identify the anode and cathode for the voltaic cell. Write out the individual half reactions that occur and write out the overall redox reaction that takes place in the cell. A proton exchange membrane fuel cell. So that's just big words for this is our salt bridge. Okay? This is showing you, this symbol here is showing you that that's a voltmeter. Okay, that's not a battery. So hydrogen goes in, and we see that, you can't see this very well, but this is hydrogen as a gas. So there's lots of bubbling happening. There's electrons in here. What about on this side? This is water. This is oxygen. Okay. This is your porous carbon. So these are inert electrodes. Okay, so which one is your strongest oxidizing agent? What are we looking at? We're looking at hydrogen coming in, and we're looking at oxygen coming in. So let's look at hydrogen and oxygen. When we look at our chart, where do we see what?
Let's see. Hydrogen's at 0, and
Oh, I see it. Oxygen's at plus 1.23. Okay? So if I see oxygen at plus 1.23 and I see the hydrogen ion or hydrogen at 0, which one's my oxidizing agent?
oxygen.
Oxygen. So that means that this is going to be my reducing. Remember, this is spontaneous. So if once we've identified those, if this is my oxidizing agent, which half reaction is this?
Reduction.
And this must be then oxidation. Okay? Those that are struggling, don't forget this part. Okay? That's why I kept stressing, make sure you're writing that down. So since we've identified oxidation, it asks us to write down the half reaction. So hydrogen as the oxidation reaction is, how am I going to write that? It's the reducing agent, so what's going to be on the left-hand side? Look at your book, look at 0, 0.00. This is my reducing agent. H2 is a gas at 0.
2H plus.
2 electrons, right? And my oxidizing agent or my reduction half reaction is going to involve oxygen. So then, in order to have an overall balanced reaction, what do I have to do?
Times the hydrogen by 2.
Times this all by 2. So I get 2H2 plus O2 plus 4H plus 4 electrons gives me 4 hydrogens plus 4 electrons plus 2 waters. Did I get everything? Okay, and now I can cancel out what's common between both the product side and the reactant side. So this is common. This is common. So I'm left with 2 hydrogen gas plus O2 as a gas. It's going to give me 2 waters. And what is the state of our water in our half reactions? Liquid. Okay? That's what that question is asking us to do. So now we're going to look at an alkaline cell. Alkaline meaning acidic or basic?
Basic.
Basic. Okay, so again we have hydrogen on this side,
Nice.
but we see that we have water now over here. And we have electrons. And on this side we have oxygen. These are electrons. Oh, writing in black on black's not the best. Okay, so what are my species again? Hydrogen,
And
oxygen. So what's my anode side? Anode side has to be what?
The reducing agent.
Okay. So which one is the strongest reducing agent this time around?
Hydrogen.
Yeah. Oops. Oh, not plus. So you can give us 2. It's 2 electrons. Did you guys find that reaction in your book? It's up hydrogen and water.
Plus 0.4. Backbone.
Plus 0.4.
4.
That's oxygen and water. That's the reduction side. That's the cathode side. I'm looking for this one. I want you guys to find this one.
And one at negative 0.83.
Yes.
I think so.
Negative 0.83. Thank you. Okay. So then our cathode side has to be our oxidizing agent, which is going to be our oxygen. So what do we need to do to get our overall balanced reaction?
Multiply the top one by 2.
Multiply the top one by 2. Okay. So when we cross off what's the same from each side, 4 OHs get crossed off, and we lose these 2 waters, and this goes down to 2. So we have 2 hydrogen, and when we do a quick check, we see 4 hydrogens and we see 2 oxygens, and we have a balance left to right. Okay? Okay, when we look at this one here, it tells us that this metal here is porous carbon and that this metal here is porous carbon. And why can we not do this kind of reaction with metals? Look at our look what's in our half reactions. Why could we not do this with metals? Nope. What do we see in our half reactions that would cause an issue with metals?
Because they're gases. Metals are solid.
No?
You'd get a metal halide, wouldn't you?
You'd get a metal
hydride.
halide. Right?
Metal
We have
hydride.
hydrogens in here, which makes it what kind of environment? Or we have hydroxides in here.
Oh, acidic or basic?
Acidic or basic, and so your metal hydrides, we looked at this in Chem 20, what happens when we put metal in with an acid? What do we see?
Bubbles.
We see corrosion, we see what?
Bubbles.
Bubbles, we see gas being generated. Chris put his hand up.
Just a minute.
Okay? So in order to avoid that, we use what are called inert electrodes. Okay? So these are reactions that don't involve a metal, and so typically they're going to use platinum or they're going to use carbon. So if you see PT or a C, you know that they're using an inert electrode. So here's lead with 2 iron 3 chlorides, gives us 2 iron 2 chlorides and lead 2 chloride. So we have to go all the way back to the basics. What is the oxidation number on lead? 0. Iron 3 plus?
Plus 3.
Plus 3. Chloride?
Minus 1.
Okay. Iron 2 chloride?
Plus 2 for the iron.
Minus 1.
Negative 1. And lead 2 chloride?
Plus 2.
And
Minus 1.
negative 1. So we see lead going from 0 to plus 2. What is that?
Loss of electrons.
Loss of electrons. And we see iron going from 3 plus to 2 plus. What's that?
Gain in electrons.
Gain of electrons.
Good call.
So we can already tell which side's going to go on the anode side and which side's going to go on the cathode side because we've identified our reducing agent and we've identified our oxidizing agent. So looking back in your notes, which one is going to be on which side?
Would PB be on the anode side? Because it's the
Yeah.
reducing agent.
Because it's the reducing agent. So that means it's going to be on the cathode side. Okay, So we've done quite a bit of the work, and we haven't even really done anything other than identify oxidation numbers and reducing agents and oxidizing agents.
Yep.
So oxidation is going to see lead going from Pb as a solid, so Pb2 plus 2 electrons. And we see reduction being Fe3 plus 1 electron going to Fe2 plus. Okay? So this means that lead as the solid is the anode. But here we have no metals, right? No metal for the cathode because it's still in ion form. Otherwise, we wouldn't be able to complete our cell notation. So if I wanted to write this out at cell notation, we have anode, electrolyte, salt bridge, or porous cup, electrolyte, cathode. So what do we see on the anode side? What is our anode?
PV solid.
PV solid. And our electrolyte?
Cl minus or what?
Nope. Lead went from lead to lead 2 plus. And then we have here for our electrolyte, we have iron 3 plus, and we're going to have iron 2 plus because we don't get a metal forming. And so then for our cathode, we could write, let's pick platinum because we got lots of money in our pocket. Okay? Does that make sense?
Sure.
So for
Sure.
that one, we have to just throw in any,
Pardon me?
for that one, we just throw in any like cathode that we think will work.
You have 2 to choose from. You have platinum or
But it
carbon.
doesn't matter which one we pick.
Nope, it's just a stick of carbon goes in there. Okay. Platinum is expensive, but it's inert. Carbon is very plentiful, but it's not as, it doesn't have the longevity that platinum has. So you have to weigh when you're doing your cost analysis, what do you need? Do you need longevity out of your electrode, or do you not need longevity? Okay, so let's look at this voltaic cell. Write the half reaction, I'll tell you what it is. I'm just going to write it down here, the voltaic cell. Okay, this is our voltaic cell. Carbon, iron species, dichromate species, and then carbon. So it says write the half reactions in the overall redox reaction that occur and then draw the diagram. So it is always written anode, electrolyte, salt bridge, electrolyte, cathode. that format never changes no matter what we're looking at. Anode, electrolyte, electrolyte, cathode. So when we look at this cell notation, our anode must be
Carbon solid.
carbon solid. And our electrolytes must be
Fe2 plus Fe3 plus.
Fe2 plus and Fe3 plus. And so our electrolytes are Cr2O7, 2 minus, hydrogen ion, and our cathode is carbon as a solid. So if this is the anode, what reaction is this?
Oxidation.
Oxidation happens at the anode, and reduction happens at the,
Cathode.
okay? So if this is oxidation, this iron species is our Fe2 plus must then be our reducing agent. And when we look over here, when we see this, this is our reduction, so this must be our oxidizing agent. So then we just need to look for chromate, since it's on top.
So why would you not look for like hydrogen?
You can, but chromate's higher than hydrogen.
So it just doesn't
Dichromate,
matter?
sorry. Pardon me?
Is that why you do Fe2 plus instead of Fe3 plus then?
Yep. Well, they're in the same line,
Yeah.
right?
Well, that's why you do like Cr2O7 before hydrogen, right?
Yes.
Okay.
And then when we look for our reducing agent, we see that we have point plus 0.77. We have Fe2 plus. Plus 1 electron. So we have to, so now we've written the half reactions. Now we need to write the overall redox reaction. So what's the next step that we have to do?
Balance electron.
How am I going to do that?
I multiply the bottom by 6.
Multiply the bottom by 6. Okay, that's our overall balanced reaction. Now part B says draw it. So it's spontaneous, so we need 2 separate beakers. Attached by a salt bridge. And we go back to our cell notation, and it tells us what we need. We need this to be carbon, and we need this to be carbon, and it's got to be connected by some way to measure that there's an electrical transfer. this is very key. This messed up everybody the first year on their diploma, so Tyrone and Colin's class. Don't get hung up that anode is drawn on the left and cathode is drawn on the right. Do not get hung up on that. Pay attention to electron flow. That's going to be critical, because electrons flow from the anode to the cathode. If the electron flow is in reverse, then this side is the anode and this side is the cathode. We write it this way because cell notation puts anode on the left and cathode on the right, but that does not mean we have to draw it that way. So please, please, please pay attention to electron flow. Okay? That's like the biggest hint, tip I can give you. Don't get hung up that this is anode and this is always cathode. Okay, so electron flow is going this way. This is anode, having said all that, and this is cathode. So what happens at the anode? Which reaction?
Oxidation.
Oxidation. So what are the species inside of here?
Fe2 with
And
Fe3.
Fe3+. And then what are the species on this side?
Cr2O7 2 minus and some hydrogen ions.
And some hydrogen. Okay? And so what kind of bridge are we going to have? What kind of salt are we going to have in our bridge? Thick.
Potassium nitrate.
Okay? Electrons are flowing this way, so nitrates are going to flow out this way. Flows from negative to the cathode. Potassium is going to go this way. So this is oxidation. And this is reduction. Okay? We're going to stop there.
Oh,
We can't, there's too much to keep going for someone to.
so much knowledge. That was a whopper of a lesson.